All right, looks like we've got quite the stack of research here. Lecture notes, academic papers, even some online demos. You really went all in on this KNN Neighbors algorithm, huh?
Well, it's a great choice for a deep dive.
For sure. So what's the plan for today? What are we hoping to accomplish?
By the end of this, you should be able to confidently discuss this algorithm, maybe even apply it.
So no, like machine learning mastery in an hour.
No, not today.
Okay, good, because that sounds way too hard.
But we can equip you with the core concepts and those aha moments that make it all click.
Love those aha moments. So let's start with the what. What exactly? ISKN. I see these visuals with colored dots.
Yeah, imagine a graph, right? And it has all these data points scattered across it.
Okay, I'm picturing it.
And each point is assigned a color, representing a category. So you drop a new point onto that graph, but this one's uncolored.
Uncolored, so we don't know what category it belongs to.
Exactly. KNN helps us figure out, well, what color should that new point be?
How? By, like, looking at the points around it?
Exactly, you got it. You look at the K closest dots to our new dot. Basically, like, taking a vote.
So K is the number of neighbors we consider.
Yeah. And whichever color has the majority among those neighbors, that's what we predict our new point should be.
So if most of its neighbors are blue, we say, hey, you're probably blue too.
Exactly.
Okay, that makes sense. It's kind of like a popularity contest for data points.
You could say that. And what's interesting is that KNN is an instance-based learning algorithm.
Instance-based, meaning?
Meaning it doesn't try to create some complex model up front. It just remembers all the data points.
All of them?
Yep. And when it needs to classify something new, it compares on the fly.
Okay, so how do we determine closeness between these data points? I mean, we can't just eyeball it, can we?
You're right. We need something more precise. We use what are called distance metrics.
Distance metrics, math.
Right, yeah, math comes into play. One common one is Euclidean distance. That's the straight line distance between 2 points. You might remember it from geometry.
The Pythagorean theorem, all that jazz. But I see other metrics mentioned too. Cosine distance, for example. When would we use that instead?
So sometimes the straight line distance isn't the most relevant measure of similarity.
Okay.
Cosine distance, it focuses on the angle between data points.
So it's not about how far apart they are, but more like the direction they're pointing.
Precisely. It's super useful when dealing with data where the direction or orientation matters more than just the magnitude. Like analyzing text documents, for instance.
Huh. So two documents could use totally different words, but still be considered close by cosine distance if they're conveying similar ideas.
Exactly. That's the beauty of having different distance metrics. We choose the one that makes the most sense for the data we're working with.
Makes sense. So we've got our data points, we've got ways to measure how close they are. What about this K value, though? The number of neighbors we consider. How do we choose the right K?
Oh, that's crucial. You got to get K right.
Why? What happens if we mess it up?
Well, if K is too small, you're vulnerable to noise. Just one outlier could throw off the whole classification.
Like judging a whole neighborhood based on one grumpy neighbor.
Yeah, pretty much. But then if K's too large, we oversimplify. Miss important nuances in the data.
So how do we find that Goldilocks K value? Not too big, not too small.
One way is to use a validation set. Basically, you set aside some of your data, test different K values, see which gives the best results.
A little trial run to fine-tune things?
Right. Now, think about those colored dots on our graph. A lot of times, they're like clustered together, right? Based on their color.
They're little data neighborhoods.
Exactly. And even though KNN is simple, it actually creates boundaries between these clusters.
So like invisible fences separating the different categories.
You got it. They're called decision boundaries. And one of the papers you gave me even had a link to a Wolfram demonstrations page that visually shows these boundaries forming. Pretty cool stuff.
Oh, definitely checking that out later. I love visuals. This is all making a lot more sense now. But I have to ask, can KNN actually be good at classifying things? Like, how accurate can it get?
That's a great question. And it leads us to something called the Bayes optimal classifier.
That sounds intense.
It's this theoretical idea. Represents the absolute best any classifier can do.
The ultimate champion of classification.
You could say that. And here's the good news. The research actually shows that as you give KNN more and more data, its error rate gets closer and closer to this optimal classifier.
So more data equals better accuracy. That's encouraging.
It is encouraging. But there's always a but.
Uh-oh. What's the catch?
The catch is something called the curse of dimensionality. And yeah, it sounds as ominous as it is.
Lay it on me. What's the curse?
Basically, when we have lots of features or variables to consider, that's high-dimensional data, things get tricky. The amount of data we need grows exponentially.
Exponentially. That's like a lot, a lot.
It is. Think about our data points again. In higher dimensions, they spread out, like they're drifting apart in a vast empty space.
So finding meaningful neighbors becomes a lot harder.
Exactly. Like trying to find your closest friends in a city with billions of people.
So is KNN doomed in these high-dimensional situations?
Well, not necessarily. There's hope. And it lies in something your research mentions, the hidden structure of real-world data.
Hidden structure. Tell me more.
Real-world data, it often has these patterns and relationships that can effectively reduce the dimensionality.
Like secret shortcuts through that vast data space.
You got it.
Can you give me an example?
Sure. Think about object recognition in an image. An image has a ton of pixels, right? That's high dimensional. But the object's orientation, it usually boils down to just a few degrees of freedom.
So even though it looks high dimensional, it's not really playing on a level playing field.
Right. And your research also mentioned facial recognition. Tons of features, but they're not all independent. Certain features tend to appear together, creating those underlying patterns KNN can use.
Fascinating. So these hidden structures, these relationships, they offer a glimmer of hope for KNN, even when we're dealing with complex data.
Absolutely. It's a big reason why KNN, even though it's so simple, it's still powerful and relevant.
Okay, starting to get why this algorithm is so widely used. But what about its limitations? My research mentions that it can be computationally expensive, especially with large data sets. Can you elaborate?
You're right, it can be. The basic way KNN works is it calculates the distance between our new data point and every single point in the training data.
Every single one?
Every single one. So if you have a massive data set, yeah, that can take a while and a lot of computing power.
It's like trying to find the closest grocery store by measuring the distance to every single store in the entire country.
Yeah. And the time it takes, it increases as both the number of data points and the number of features increase.
Right. More data, more features, more time. But that brings us to this section I'm seeing on fast KNN. Are there ways to speed things up?
Absolutely. There are some very clever techniques for that, and that's what we'll dive into next.
Okay, I'm ready. Let's make KNN fast.
Okay, so we left off talking about how those KNN calculations can get pretty slow with large data sets. You mentioned there are ways to speed things up, though, right?
Yeah, there are a bunch of the techniques for fast KNN.
Fast KNN, I like it. So what are some of the tricks?
One really common one is using KD trees.
KD trees, what are those?
It stands for K-dimensional tree. It's basically a way of organizing the data so we don't have to, calculate the distance to every single point.
So instead of brute force searching, we get a little roadmap to guide us to the nearest neighbors.
Exactly. A KD tree, it divides the data space into regions, makes the search much more efficient. Like imagine trying to find a book in a library.
Okay.
If the books are all just scattered everywhere, you'd have to check every single one, right?
Nightmare. Total nightmare. But if they're organized by subject, by author, you can narrow down your search super fast.
Makes sense. So it's like having a Dewey Decimal System for data points.
Right. So KD trees can really help with speed, but there are a couple of caveats.
Caveats, always caveats.
Well, yeah. Building the KD tree itself, that takes some time up front.
An investment.
Right. And then remember our friend, the curse of dimensionality. In very high dimensions, even KD trees can struggle.
So they're not a silver bullet, but a good tool to have in the toolkit. What other speed-boosting techniques are out there?
A whole bunch. There are some that, approximate the newest neighbors instead of finding the exact ones, sacrificing a bit of accuracy for a big speed boost.
Interesting trade-off.
Yeah. And there are other clever data structures, too, things like ball trees or locality-sensitive hashing. Each has its own, strengths and weaknesses.
So choosing the right one depends on the data and what we're trying to do.
Yeah, exactly. No one-size-fits-all solution. But speaking of real-world data, it's rarely perfect. So what about, missing values? Or what if we get ties in the classification?
Does KNN just fall apart?
No, it's actually pretty robust. For missing values, we can often fill in the gaps using, the average value from similar data points.
So if we're missing the price of a house, we could estimate it based on the average price of other similar houses in the neighborhood.
Exactly. And for ties, let's say our new data point has an equal number of red neighbors and blue neighbors.
Tough call.
Right. Well, we can use prior knowledge, maybe we know that red is just way more common overall in the data set.
Okay, so a bit of context helps.
Yeah. Or we could reduce the value of k, really focus on the very nearest neighbors and see if a winner emerges.
A tiebreaker round.
Yeah.
So KNN can handle the messiness of real-world data. That's good to know. Now, what about those decision boundaries we talked about? What shapes them?
Well, the distance metric we choose, it actually plays a big role in shaping those boundaries.
Really? How so?
So, Euclidean distance, being a straight line measurement, it usually leads to circular or spherical decision boundaries, like drawing a circle around each data point.
Everything within that circle belongs to the same category.
Yep. But with other metrics, like cosine distance, we can end up with way more complex boundaries. Curvy, weird shapes. Because cosine distance, it cares about the angle between points, not just the distance.
It's like using different drawing tools. A compass versus a freehand pencil.
That's a great way to think about it. And that's why KNN is so cool. It can capture these really interesting patterns and relationships in the data.
It's more than just a simple voting scheme.
Way more.
Okay, so much to unpack here. But can we talk about where this algorithm is actually used, like in the real world?
Oh, it's everywhere. Your research had some awesome examples.
Hit me with them.
Recommendation systems are a big one.
Like Netflix suggesting what I should watch next.
Exactly. It looks at your viewing history, finds users with similar tastes, recommends stuff they liked. It's also used a lot in medical diagnosis.
Oh, wow.
Yeah.
How so?
Well, it can help doctors classify diseases based on, patient symptoms, medical history.
A team of virtual doctors helping to analyze data. That's amazing.
And then in finance, you've got credit scoring. Banks use it to, assess the risk of lending money to someone.
So it's kind of like a data-driven crystal ball predicting if someone's likely to default on a loan.
Pretty much. KNN is really good for those kinds of predictions.
Okay, so KNN is versatile, powerful. But my research also mentions some limitations. We talked about the curse of dimensionality and the computational cost of dealing with tons of data. What other trade-offs should we be aware of?
Well, KNN can be sensitive to noisy data, if our training data has errors or outliers.
Garbage in, garbage out.
Yep, exactly. The quality of the data really matters. And then another thing is that KNN doesn't actually learn a model from the data, it just memorizes it.
So it's more like a massive lookup table than a complex equation.
Kind of, yeah. Which has its advantages for sure. It's simple, right? Easy to implement. And you can easily add new data points without retraining a whole model.
Flexibility points.
Right. But this approach, it also means it can be computationally expensive to store and search through all that data, especially for real-time predictions.
So always trade-offs.
Always. But hey, we've covered a lot.
We have, from the basics all the way to the nuances. Before we wrap up, is there anything else about KNN we should touch on?
Actually, yeah. There's this one key aspect that I think is really important, and it often sparks some debate. It really sets KNN apart from a lot of other machine learning algorithms.
Okay, I'm all ears. Tell me more.
So it's all about how KNN doesn't actually create a model.
It doesn't.
Nope. A lot of machine learning algorithms, they try to generalize from the data.
Right, find the patterns, build some equation.
Exactly. But KNN, it doesn't do that. It just stores all the data points and chills until it needs to make a prediction.
So it's not building a set of instructions, it's more like a giant memory bank.
Yeah, that's a good way to put it. It remembers everything and then just compares new data to its stored memories.
Huh. So what does that mean for how it works, how well it works?
Well, it makes KNN super adaptable.
Adaptable how?
If we get new data, we just toss it into the memory bank.
No need to retrain a whole model.
Exactly. And it's also transparent. If we want to know why KNN made a certain prediction, we can trace it back to the exact data points that influenced it.
So it's like having a clear audit trail for the algorithm's reasoning.
Yep. But of course, there are trade-offs. This lazy learning approach can be computationally pricey, especially with a ton of data and if we need predictions in real time.
Right. Got to store all those memories.
And it can be sensitive to how we choose K, the number of neighbors, and the distance metric.
So those choices really matter.
They do. If we choose poorly, our predictions could be way off.
Okay, makes sense. So, big picture, where do we stand with KNN? We've seen how it works, the good, the bad.
I think it boils down to this. KNN is a powerful tool. Maybe deceptively powerful? Well, it's so simple, right? But it has a huge range of uses, and when you pair it with the right techniques and really understand its quirks, it can be incredibly effective.
I have to say, I've learned a lot today. I had no idea how much was going on behind this seemingly simple algorithm.
Glad to hear it. But remember, this is just the tip of the iceberg when it comes to machine learning.
So much more to explore.
Exactly. Keep that curiosity burning and you'll never stop uncovering fascinating stuff.
You've definitely sparked my curiosity. Thanks for guiding me through all of this.
Happy to do it. Always a good time to chat about KNN.
And to our listeners, thanks for joining us on this deep dive. We hope you've learned something new or at least had your curiosity piqued. We'll be back soon with another deep dive into the world of algorithms and data. Until then, keep exploring.